All right, thank you for your patience. As you can see, I have the button down on today, so it was an important meeting that I had to be at. But other than that, we'll end at the normal time. Any questions before we get started? So today we're going to continue on with this diazotization reaction. That's going to allow us to get these other heteroatoms onto the ring. So we'll learn about fluorine, iodine, oxygen. We'll also put another reagent on there, a nitrile group, using this chemistry. So as a refresher, we're taking benzene, we're nitrating it, we're doing a reduction to the aminobenzene, and then we're further going to transform that into this diazonium. So this is actually a reactive intermediate. It's not typically a product that's isolated. So what I'm going to do is put a bracket around it. And that means you make it and then use it, and we say in situ. So you make it, immediately use it. It's not something you isolate or store for an extended period of time. And the reason for that is that N2 plus. Let me just expand that out. And that's what the N2 looks like. And so N2 is diatomic nitrogen, so nitrogen gas. And really what that is, it's now a good leaving group, so you can substitute it. So the reason the temperature is kept at 0, if you heat it too high, it'll just spontaneously evolve nitrogen. And then other decomposition pathways happen. So you make it, I'll run through some mechanistic stuff, and then what do you treat it with? So this is an electrophile. We're going to treat it with those heteroatom nucleophiles. And apologies for pre-filling out this slide, but it's just rewriting what we talked about last week. I'll briefly run through it. And then on the next slide, I'll show you how we're using this intermediate. So NaNO2 is sodium nitrite, aqueous HCl. So aqueous just means it's a solution in water. So if this is a salt, we have water, it dissolves, and then the HCl allows the mechanism to proceed to generate nitrous acid, so HONO. And then we get sodium chloride as the inorganic byproduct. The nitrite will abstract the hydrogen from the HCl, and that generates the nitrous acid, and there's your byproduct. So you can't buy nitrous acid, so you're making it in the pot and then using it. And so it's not exceptionally stable. So it turns out that the hydroxyl group will get protonated by the excess HCl. And that allows for the formation of this thing here that looks almost like water. So a lone pair on oxygen will push down through an elimination and then expel water as the neutral component. And then you end up with this NO plus, and that's the nitroso ion. So it's an electrophilic nitrogen. And then this is just the resonance forms of it. And then the Cl balances out the charge, so you're neutral. So we're going to use that NO plus to react with our aniline. And so that's the mechanism we'll write on the next page here. sorry. Should be plus there. So remember, we're still under these conditions of HCl aqueous, because I'm going to invoke that through this. So with the amine of the aniline, the nitroso ion and HCl, if you look at what do we need to do in terms of writing the mechanism, this nitrogen now needs to become bonded to another nitrogen, and that's where we invoke the nitroso ion. If you look at the two reactants, what's changing is H2 and then O. So we have to remove the two H's from the one nitrogen and then the oxygen from the other. And so in a sense, it's a condensation that produces water and then allows us to form that reactive intermediate. So we know that the amine has a lone pair. And this is where things can kind of look weird. We're going to have that lone pair attack that nitrogen. And the driving force for that is to break that, one of those pi bonds of the triple bond, so that the oxygen gets its two lone pairs of electrons and becomes neutral. So finishing off all the charges in there just so we can see where things are going. We'll just have that Cl minus grab up a proton and make the amine now neutral. I guess I could show the next thing maybe two ways. I want to show you one way, and then if that's not clear, I'll draw the other way. The relationship between the nitrogen 1, then you have nitrogen 2 and oxygen 3. The hydrogen atom can shift from that nitrogen to the oxygen, and that's called tautomerism. Again, alternatively, we could show it as just a series of proton transfers where the oxygen gets protonated by HCl, and then we have that resultant Cl minus just abstract the proton from nitrogen. But this is ultimately what would result from that as well. So tautomerism is not resonance because the proton's moving. And so we're almost there. We have the nitrogen bonded to the second one. We're starting to look like we could form water and get rid of that oxygen. So we'll go ahead now and protonate the oxygen. And at this point, the driving force for the formation of this is the nitrogen that's bonded to the ring is going to do an elimination. So an elimination always forms a pi bond. So these electrons will push in to form the triple bond, and then we would expel out water. So that oxygen gets its second lone pair. And now we've formed the nitrogen-nitrogen triple bond, which has a plus, and then the chlorine will balance the charge to give us the neutral species overall. And as we progress through this semester, we're going to do a lot of proton transfers and things. And that will translate into your biochem courses if you go that route. In terms of how aqueous systems work, how do reactions take place in enzymes, there's always a lot of proton transfers. So typically, you're looking at basically shuffling a proton around from some heteroatom so that you can make things a good leaving group. And that's what we've done with the oxygen, starting from this nitroso ion. We're essentially working it towards water so that we can get rid of it. And like I said, now that we have this, we can think of that N2 as wanting to be nitrogen gas. So it wants to leave that ring. So this is an electrophilic carbon that we can start attacking with nucleophiles. So it'll attack, substitute, and then nitrogen will get evolved. So the next couple of slides are going to show you the reagents you can use, but forming the diazonium is going to be the same for all of them. So to get fluorine into the molecule, making an aryl fluoride, we're going to use this reagent, which is called tetrafluoroboric acid. Since boron's electron deficient, when it adds that fourth substituent, it becomes negative. And so you can almost think of this being equivalent to like F minus. So that would be nucleophilic fluorine. And so what would happen, we're going to add that fluorine. It's going to break the pi bond. So the carbon is going to have a carbon-fluorine bond and a carbon-nitrogen bond. Then we'll put a lone pair into the ring. And that lone pair will collapse to re-aromatize. So this just comes down to reform that bond. And now that second nitrogen gets its lone pair to form N2. And sometimes if the reaction is like really vigorous, you will see frothing or bubbling at the surface of the liquid. And so now I'll highlight in blue. So there was the carbon bearing the amine, the aniline group. And so a way to think about this is anytime you see like an aromatic fluoride, if you think backwards, that is ultimately coming from a nitration reaction, because you have to go through these steps to get there. So as drawn on this slide, that mechanism is called SNAR, so substitution nucleophilic aromatic. And because an existing group is being substituted, this word ipso is used. And that's just terminology specific to this class. I don't think I use ipso in my everyday conversations at all. So that's what it means here if you were to see it in something that matters.
Wait, what does it mean again? Sorry,
It might be Latin or something. I think it means same.
Okay.
So ipso means same. Like this existing group is ultimately being substituted for something else. So again, that's how you get fluorine in, because we can't use F2. You have a question?
Yeah, is it because like fluorine is a stronger nucleophile?
Well, if we're going back to, chlorine versus bromine, those are sufficiently electrophilic. I think with F2, in general, those F2 itself tends to be pretty reactive, and it would probably just chew the molecule up in a sense. So F2 is probably too reactive and I2 is not reactive enough. So if we wanted to get iodine, we'd make the same diazonium, and now the reagent we would use is potassium iodide, so just your normal inorganic salt. And remember, since we're under aqueous conditions, H2O, that solubilizes the Ki. And the SNAR mechanism would be the same. So it's an addition of the nucleophile. You have that carbon di-substituted, and then an elimination to re-aromatize. So just a brief comment. In mass spec, chlorine and bromine have the signatures. Iodide isn't, as prominent, but sometimes you can see a signal at 127, and that's typically like I plus or I minus. You're seeing the iodide itself. And so that takes care of the group 7. Those are the halogens. We talked about getting nitrogen on through nitration. How do we get oxygen on? In general, getting oxygen onto a ring, like synthetically, is not easy. Biologically, with enzymes, that's kind of what your liver does. That's how it sort of takes care of things. The reagent that we use for this process is copper oxide, so Cu2O. So really, it's a form of like O minus. Notice it's not hydroxide, it's just oxide. So again, because you're in acidic conditions, ultimately this H does come from the acid HCl. But the oxygen is going to come from that copper oxide. And so we know by now that through IR, the OH stretch has a unique signature to it. How to identify it? That's how we know we've correctly installed it. So one other thing, phenol. Because of the lone pairs there, that is an ortho-para director. Any questions?
Could you remind me which one is it with the number on the ring that it is?
So remember this ortho-para or meta nomenclature. It's only valid for di-substituted aromatics, where you only have two substituents. We'll draw all these things out a little bit later in today's lecture. And then once you get three or more, you can't use that nomenclature anymore because it's specific to just two substituents. So ortho means 1, 2, meta is 1, 3, and para is 1, 4. And so the last reagent is going to install carbon, but a specific type of carbon. The reagent is copper cyanide. So it's a negatively charged carbon, so in essence it is a carbanion. But the important thing that I've noticed or I've written here, that 3, that's the oxidation state of that carbon, oxidation state 3. So we're counting the number of bonds to the nitrogen. So as a refresher, an sp hybridized carbon at oxidation state 3. And because it has those double bonds, it's a meta director. So a 1,3 director. And in the IR at region 2 is the triple bond, so you would see a nice, strong, sharp signal from 24 to 2200. When we get into the next, module 2 and 3, we'll start talking about oxidation states more. And so oxidation state 3, so this molecule, that carbon is also at oxidation state 3. So it's called benzoic acid. Because the carbons are the same oxidation state, we call them equivalent. So you're not doing an oxidation or a reduction if you go from one to the other. Yeah.
Is that why the carbon that is bonded to the carbon in the carboxylic acid, is that why it doesn't affect the oxidation state?
Yeah, because we're just counting those. So we're counting these number of bonds. So 1, 2, and 3.
And And you don't include the one connected to the carbon within the ring?
No, because it's not a heteroatom.
Oh, okay.
So we'll learn reactions where you can go back and forth between these. And that's useful, keeping the equivalency of the oxidation state the same as we start tacking more reactions onto sequences. I lied, there's one more. Maybe two, I don't remember the order here. So this slide is called deuterium labeling. So deuterium is the question or stretching? Deuterium is the stable isotope of hydrogen. And so hydrogen has an atomic mass of 1, deuterium is 2. You can get the deuterium atom using this reagent here, D3PO2. The regular version is called hypophosphorus acid. And it has kind of a weird looking structure where even though it says acid, the H or the D atom is behaving as a hydride. So H minus or D minus. So if I draw that out, pretty sure it looks like that. So phosphorus is right below nitrogen, so they have the same sort of bonding pattern. This phosphorus is oxidized, but it's at the lowest oxidation state. That's where the OUS ending comes from. So you're probably more familiar with like phosphoric acid. And so overall, what are we doing? You've put that nitrogen on the ring, but here you're removing it completely. So this is another, you could say, why would you want to do that? Well, you have to get it on there through nitration, which is substitution for H for nitro to begin with, and now you're removing it. So as I said, when we start looking at more complex substitution patterns, you'll have to put things in to like direct and then remove them because all they're doing is blocking a position. And then the deuterium will obviously add another mass unit. So it's a way of like looking at a structure, and if you say, I want a deuterium atom right there, this is how you would do it. Any questions? Yeah.
What is the reason why you put the deuterium in the bracket?
Oh, it's just like it can be H or D, either one.
It depends on what reagent we're using.
Yeah, if you're just using the regular H3PO2 or the D3PO2. So here's this type of question where you have the diazonium salt, and then you're going to treat it with some, nucleophile to do that substitution, based on the IR spectrum, what reagent was X. So A is the correct response because we see that big signature there, that's our OH group. So again, that one does kind of look like a thumb, so it sticks out like a sore thumb. And so the same set of reagents now, but the spectrum's different. So what stands out to you in this spectrum?
Triple bond.
The B at 3,200, the B answer.
This one you're talking about? I heard someone say triple bond. So yeah, that is a triple bond. So that's the nitrile. So that region between 24 and 2200 is your triple bonds, and then that would come from the copper cyanide.
Where does that peak also come from? The between 3,000 to 3,200?
This stuff.
Yes.
SP2 like
So remember that because this is organic, all your molecules are going to have CH bonds. So that stuff will always be there. Any questions? Okay, so based on our learning so far, we know how to get these heteroatoms onto the ring. The copper cyanide allows us to get a carbon onto the ring at oxidation state 3. What about the other oxidation states? How do we do that? The two named reactions that we'll learn for this are called Friedel-Crafts reactions. And I'm going to start with acylation. And let me give you a sort of a brief introduction to what that means. If you look at the electrophile here, that structure so we have 3 carbons, and then it's an acid chloride. The oxidation state of the carbon is 3. And then maybe I'll do it in blue here. Everything, including the carbonyl part of that, is called the acyl group. So an acylation is putting on the acyl group to the ring. So our electrophile is this propiononyl chloride. We have a Lewis acid aluminum trichloride that we saw with when we were using chlorine to get chlorine onto the ring. Yeah.
Can the electrophile be any number of carbon chain?
Yeah, it can be anything. Yeah, so you need this part, the acid chloride part, but all of this stuff that's attached to it can be whatever. So we're substituting the H for this entire acyl group. And then if you look at what is the major functional group, we're making a ketone. So a Friedel-Crafts acylation makes a ketone. If you look at the difference between the electrophile and the product, the electrophile is at oxidation state 3. It has a chlorine. That chlorine is no longer in the product. And that carbon has gone down an oxidation state because it lost that chlorine. If benzene is our nucleophile, the acid chloride is the electrophile, but then there's this aluminum trichloride in there. So how do those two react to form this intermediate that will do this electrophilic aromatic substitution. And that intermediate is called an acylium ion. So the next slide, I'll show you where is that chlorine going. So just another sort of thing. IUM typically means a positively charged intermediate. So the question was, what is the nature of this? So B is what we're starting with. The intermediate has to be positively charged. So that would rule out C. And then, so we're now between A and D. So what is exactly happening? We know that aluminum is electron deficient. It's showing 3 bonds, so it doesn't have an octet. It has that p orbital that's empty. So what will happen is a lone pair from oxygen will come down, and it will eject out Cl minus, and that Cl minus will go into that p orbital of the aluminum. So now we have a carbon-oxygen triple bond. The oxygen's plus, and the aluminum would be minus. And that's our acylium ion. And so the same electrophilic aromatic substitution mechanism happens. The benzene ring attacks that. You then do elimination of the H to restore your aromatic stability. And so the thing to remember is that carbon that's now bonded to the ring is a ketone, oxidation state 2. We can use the resonance argument to understand why a ketone is a metadirector. But now, since we have an oxidized carbon, we can do a total reduction. And the conditions that are listed here are called the Clemmensen. Does anyone know who Hans and Franz are? Showing my age here. Do you know what Saturday Night Live is? Okay, so now imagine Saturday Night Live without Adam Sandler. So this is back in like the early 90s. Hans and Franz were these two like weightlifter guys. They said, listen to me now, hear me later. So we're at this oxidation state, and we can manipulate it. So this specific type of manipulation, it's a named reaction. So we're going to learn a lot of named reactions. So when I say Clemmensen reduction, the association you have to make is with the conditions listed. And when we get into module 2, 3, and 4, we're going to learn all sorts of named reactions, like aldol, Claisen. You already learned like Diels-Alder. So from that name, you should have an idea of what's happening. So the reagent, or the reductant in this case, is this. So zinc and mercury. And so that's called an amalgam. If you have like silver fillings for your cavities. That's an amalgam. It's a mixture of two metals. So if you normally take two solids and mix them, they're going to have like not equal composition throughout, right? But in this case, because mercury is a liquid and you add the zinc, you get a nice homogeneous mixture out of it. And so when that solution, it's called an amalgam when they're solids. So that's supplying some electrons. The HCl is supplying some protons, because if you look, we're going from oxidation state 2 all the way to 0, meaning that carbon is getting 2 hydrogens. And then this would be run under aqueous conditions. So the zinc mercury amalgam supplying some electrons. We're not going to worry about the exact arrow pushing here, but it's going to reduce that 2 all the way to 0. So we have a meta director. We're removing the electron withdrawing group, and now we're ending up with an ortho para director. And the other main thing I want to point out about this strategy you notice your aromatic ring, but now the stuff bonded to it, that side chain, it's completely linear. This is, if you want a linear side chain, you have to go through this strategy, the Friedel-Crafts acylation and then reduction. And I specifically point that out because on the next reaction will always give you a branched side chain. Questions? Yeah.
How do you determine the difference between meta and ortho and para?
So on this side, when we're looking at that, first you're determining it based on the substituent. So that substituent here, the carbon bonded to the ring is the benzylic carbon. The carbonyl functional group, through this resonance argument, is putting that plus charge at the benzylic carbon. We can also draw more resonance structures where the plus charge goes into the ring. And so that's going to say, okay, this is meta. Now, since we reduced that, this carbon, it's electron donating, but through induction, and that's through the bond. And I'll clean up the structure here a little bit. So through bond is typically drawn with just like little arrows, because it's not resonance. You're not pulling that pi bond density out or anything. It's just strictly, the electron density in the bond can go into the ring. Because it's pepping up the ring a little bit, now it's an ortho para director. Another way of doing that reduction is a two-step process where, again, I can't sort of talk about everything at once. So this is a little preview of, say, module 2. Getting my dates confused here. See this oxidation state 2? Notice in the product here, it's still at 2. But what's the difference? So sp2, sp3. The oxidation state's staying the same, but the functional groups are changing. So it's an equivalency. So under this first set of conditions, this molecule here is essentially losing water. So you have H, H, and O. It's swapping that out to put in, instead of one heteroatom, now two. We started with a carbonyl, and this is called an acetal. And now we can reduce that. So hydrogen gas, nickel, and methanol will achieve the same transformation. And why do these alternatives exist? When you work with heavy metals, zinc and mercury, there's environmental issues, toxicity issues, but practically speaking, they can be kind of a nightmare. Sometimes they'll form emulsions or froth and things like that, and they're just really difficult to manipulate. So this is an alternative reaction. And in terms of the name, I would just call it a Rainey nickel reduction. So Professor Rainey was, I think, at the University of Nebraska or Oklahoma. He found a way that you could treat nickel to make it really reactive to do this type of reduction. Yep.
Is there a reason why anyone would want to do the zinc mercury one over this one?
So I would say probably not. I mean, why is it in your textbook? I mean, everything in your textbook is like 75, 100 years old. I mean, it's what you're learning now is not the state of the art in terms of organic chemistry. So you're learning like historical reactions. And so the reason for that is you learn the foundational stuff. The state of the art stuff, it can get pretty complex. But if you don't understand, these more straightforward historical reactions, the newer stuff people do now it's hard to understand. So that's, again, another way of doing it. So the acylation gives you the ketone. Now the Friedel-Crafts alkylation, so that, again, the word changed. It's installing the carbon side chain with no oxidation state. So a couple of things to notice about this. See the electrophile we're starting with? We would classify chloropropane as a primary chloride. You see where the chlorine starts, and then you see where the bond to the ring is formed. So the issue with the alkylation reaction is because you're going through an electrophilic intermediate, so a positively charged carbon, carbocations rearrange. So that's essentially what's happening. So even though you start with a primary chloride, the reactive intermediate is a secondary carbocation because it rearranges. And the consequence of that now is the side chain is branched. So to put all that into perspective, whenever your side chain is linear, you have to do an acylation reduction. So if you started with that, the secondary, you would still end up with that same product that's listed. So acylation gives you ketone, alkylation gives you alkane. I've already drew the mechanism here, so I'm gonna I can blow past that. So I think the last set of stuff that we'll look at today before we end so the carbon bonded to the ring, that's the benzylic carbon. If it has hydrogens, those are benzylic hydrogens. And if you remember from organic 1, those benzylic CH, that bond is very weak. So whether you form a plus, a radical, or a negative charge there, you're able to manipulate those specific hydrogens very easily. So we would call those aromatic hydrogens. Then we have benzylic, and then this is your normal secondary, and then that's your normal primary. So the benzylic ones of all of those are the special ones because those bonds are easiest to break. And because of that, we can do a radical halogenation. Where one of those H's gets substituted for bromine. And NBS, that was N-bromosuccinimide. That's the source of the bromine. This initiator here is benzoyl peroxide. So the OO sigma bond is the peroxide bond. That will cleave pretty readily. So you get two of those benzoyl radicals. So at this point, you could either use that to abstract a hydrogen, or it could lose CO2. And now that thing's really reactive, so it scans the molecule and it says, okay, that hydrogen, I can break that bond pretty easy. And it forms a benzylic radical that will then react with the NBS to install the bromine and do the substitution. So in essence, you've taken, your oxidation state 0 and increased it to 1. So it's a way to do an oxidation, but also now this is a good leaving group. So remember your SN2 chemistry. Now you can displace it with pretty much any nucleophile. Okay, so one more slide and then we'll wrap up for today. So on the left and the right, those things are converging to the center molecule called benzoic acid, but using different reagents. So I'm going to highlight that blue carbon. I know it might be hard to see, but I'm drawing in green here the hydrogen atoms. As long as the benzylic carbon has at least one hydrogen, you can treat under these oxidation conditions, and it's going to chop off every other carbon on the side chain except the benzylic one. The blue carbon is retained, and it gets oxidized up to an acid. The mechanism of that is kind of complex. We're not going to delve too much into it other than recognizing that we can use sodium dichromate and sulfuric acid. I guess that's for both of them. The difference between is linear versus branched. But either one will converge to that oxidation state 3. So we've taken ortho, para. These orthoparas, oxidized it, and now we switched it over to a meta director. And so that's one strategy of switching the directing group ability. Then on Wednesday, what we'll do is look at some molecules that have 2 benzene rings. Where does a reaction occur? And then we'll start applying the strategy. How do we make something with 3 or more substituents? How do you control the location? And then on Wednesday, after lecture, your exam 1 will open.